All right. Hi, everyone. I'm going to reset my timer. And thanks for being here. I'm Amir. This is, I guess, a bit of an unusual or less usual inaugural lecture because I've been here for some time already, but the talk is now, like Tanya. So I'm going to mainly show things that we have done since my arrival at EPFL, so they're more recent works. So thanks for the introduction, by the way. Honestly, I was expecting much worse. But what kept me hopeful is that I wasn't sure if he has access to the material to bring it to the presentation, but this is better than what I expected. Is this cup from mine, I suppose? Oh, well, no, I'm not gonna steal yours. Yes. So yeah, now that I'm relieved from the stress of Rudiger's introduction about vision. So I'm going to talk about multimodality and embodiment in vision. And I'm going to illustrate what I'm going to show with this example. So these are two different eyes with two different pupil shapes. One of them is a predator, and the other one is an animal of prey. Do you have a guess which is which? One of them is a sheep, and the other one is a cat. So, I mean, you have seen probably cats, so you would know that the left one is the cat and sheep, but this pattern happens quite frequently. It's a high variance pattern, but the pattern clearly exists that ambush predator animals usually have vertical pupils, and animals of prey have horizontal. The question is why? The standing hypothesis is that it's probably because animals of prey, what matters to them is not dying. And so that basically means when they are grazing, they have to have a high field of view, could benefit from a high field of view vision in order to detect a predator that comes from any direction. And so, by having the opening of the eye elongated in this direction, they gain a small advantage in that sense. And ambush predators don't have that requirement, but then, because of their ecology and the vertical type of pupils gives them a greater control over the amount of light that can enter their eyes for the ecology and the occlusion patterns nearby. So, like I said, this happens relatively broadly with some exceptions. And so this indicates that basically vision is an act that is very related to the downstream objectives of an agent, the environment where it lives, and its embodiment, the specifics, and so on. So, like I said, this pattern goes more broad than pupil shape. Predators often have frontal eyes because that gives them overlapping field of view and therefore a better sense of depth that is useful for targeting. Animals of prey more often have the eyes placed on the side of their face because, again, that gives them a higher field of view, which these are exemplifications of what I was trying to describe, that the relationship, there's a tight relationship between vision, the body of the agent, the actions, the goals, the downstream environment. So sometimes motor control also comes into the picture. So you have seen pigeons, walking in this funny way, moving their head. It appears somehow unnecessary, And the one hypothesis why they are doing this is that they are not actually moving their head too much. They're moving it too little. So this is if you actually fixate the camera, what you see here on the head of the bird, you see that it actually keeps it stationary for a long period of time and then bursts forward, keeps it stationary, bursts forward. And that's because that by keeping it stationary, if you have the slow photoreceptors in your eyes, you get motion blur if you move at the same time that you're trying to look. So if you keep your head stationary, you'll get less motion blur, and this is just advantages to your vision. So basically motor control and these specifics of the embodiment came into the loop in order to optimize certain parameters of vision, and so on. And sometimes the adaptation is also less usual. So this is a fish. What you notice about it is that it doesn't have eyes, but evolutionarily speaking, they did have eyes. And the reason is that sometime at some point in the evolutionary trajectory, they migrated deep into the caves. So while they had eyes, well, deep into the caves, there's no light anymore. So therefore, there's no point in having a light, and they just lost their eyes, evolutionary speaking. And their surface cousin, which is genetically very similar, stayed on the surface and preserved the eyes. So a lot of different disciplines have looked at the relationship between vision in a more integrated way with embodiment and environment and so on and so forth. Psychologists, most commonly the ecological view to computer vision, which is by Gibson. This is about light switch theory that says that about Cambrian explosion happened because photosensitivity, sensitivity to light, and the ability to move almost appeared at the same time. So it created an arm race in terms of brain size and so on. So originally vision appeared in an action loop in order to enable an agent to have visually guided behavior and so on. So it's all about action. So these are some resources if you're interested in, very interesting books. So instantiations of this story that I've been discussing from a more computer vision, an engineering perspective, but you can think of it as that way. Schematically, there's an agent in the world. This agent is embodied, has some body that actuates its motions, and there's some sensory system. So the sensory makes an observation, gets processed by some vision system that goes into the control. That's the part that decides how to move things, how to do things with the information that has been sensed from the environment, and then goes back to the hardware. The hardware executes it one step forward in the environment, and this loop is executed again and again and again. So vision is now an integrated part of a more complete system, which includes embodiment, which includes control, which includes evaluation, the sense of success of the downstream action rather than success of the pure vision on its own. And in contrast to classic static computer vision, like object classification, which is purely a static and offline task. So you can see that the pipeline for addressing the problem in an integrated way is different than what we have. The field has learned quite well how to do the static pattern recognition tasks. So like the AlexNet paper. And since then, the progress has improved, right? Now, we commonly say that if you have a specific task that you want to solve, if you have enough data for it, it's usually expressive by neural networks, and therefore it can be learned. So we have really found a effective way to map, X to Y with enough data in a supervised way. But that's not really the full pipeline, like object classification and so on. So like I said, it's more like an integrated box into the much bigger pipeline. So in the past few years, I have worked on topics related to what I discussed, the integrating vision in an action loop. So for example, we have developed visual simulators. So simulators are basically data sets of embodied vision. We need data for learning, and so you can see that the paradigm here is completely different, right? So the agent, compared to static data sets, when you can record an image, save it in the hard drive of your computer, and that's it. In an active setting, an agent has control over what image it will have to see next. If I decide to make a left versus make a right, which is decided by me, I'll see different images. So therefore, you have to have some sort of online generation pipeline, like a simulator to generate images. You cannot just save it as pre-images. And so this gives rise to visual simulators. These are simulators that have physics, have this, for example, a humanoid robot is a particle robot that's physics. Once it hits the door, it falls and so on. So this is all integrated within a pipeline that also has a realistic data image generation part. And these are scans of the real world. These are not artificial buildings. So that's what we did back in 2018. And this was basically one of the first that ever accomplished this pipeline of having simulators based on scans of real buildings rather than artificial models. So then we use these simulators to actually learn visually guided behavior. For example, we can have a robot that plays catch with a cube, but this is communicated basically visually to it. It has to see the cube and go to it, or the ant that is climbing down a stairway based on the visual feedback that it receives. Or like we worked on what it was called mid-level vision, which was a vision module that you plug into the loop of an active agent and in order to accelerate the learning of its visually guided behavior. Okay, so these are the things that we did in the past, so I promised I will show things that are more recent. So I'm going to show something that we are just wrapping up. We have just wrapped up, and that was about simplicity. So humans have pretty good eyes in general. We don't have the best eyes. Falcons, in terms of resolution, they're better than us. In terms of low light sensitivity, of course, there are many things better than us, many animals. But we generally have one of the best eyes, so high resolution, especially in terms of resolution. So your house cat has inferior resolution to your eyes, especially inferior color vision too. And as you go down to, like mosquitoes and flies, you can see that they see very little in terms of resolution. These are all like blobs. When you look at these things, it appears almost impossible to actually do something visually useful and survive in an environment based on this resolution and that resolution. But clearly, these animals are very capable. They're basically can effectively execute whatever behavior they want to do and make it work with these things. And this shows the same thing, but in a bit more detailed. So if there's a butterfly like that to another butterfly, like namely the map butterfly, it looks like this from 10 centimeters away. It looks like that from 1 meter away, and it looks like that from 2 meters away. So it's like, if you're a butterfly, this is the level of information you receive from the environment. At least it looks like that from when you're only 1 meter away from things. And to birds that have better eyes, 10 centimeters is pretty good, but around 1 meter and 2 meters, which is not too far, it gets blurry. So clearly, these animals have made it work. So they're actually, in a way, so good that when I tell you the mosquito or fly only sees, you would be surprised that you would expect them, from their agility and effectiveness and success as doing what they want to do, that this would be more than that. So basically, when you look at nature, namely when vision is part of a particular animal's pipeline, solutions that are good enough come out. Solutions that are not perfect in any sense, but solutions that are just good enough. And it's very interesting what would be good enough, because now it's plugged into the bigger loop, and we can interpret, we can evaluate the value of a vision system. So simplicity emerges basically at interesting places. And so not just in terms of resolution, but scallops. This is like a typical scallop, and scallops have very small but large number of eyes that are distributed around the edge of the shell. So this is completely different from what we are used to, usually 2 eyes, big on the head and so on. This went with a completely distributed system. So in different morphologies, the solution was not so that all of these eyes are integrated in a grid to give higher resolution vision to an animal. It just decided that I'm going to distribute it around the shell, and again, it turned out to be probably, evolutionary speaking, useful. So what I want to frame is basically good enough. There seem to be solutions that are good enough and they're simple, and we wanted to understand where that actually can go. So inspired by that, we wanted to study basically how simple we can go in terms of resolution in robotics setting and still be able to solve downstream problems. So what we did, we basically replaced cameras with photoreceptors. So a camera, if you run your camera at a very modest resolution of 128 by 128, it has 16,000 something pixels in it. So cameras obviously have a lot more resolution than this, but this is still a modest time check. Modest resolution when machine learning is relevant. So still 16,000. A photoreceptor is a 1 by 1. It's basically one sensing point of light in the surrounding environment. So you can think of it in a simplified way as a camera with resolution 1. And so these are like cameras basically are the outcome of a very packed sensors fabricated. And they're very high resolution, obviously, because they're created for humans. And photoreceptor is something that you can do with a very simple photodiode. This is just the most like the primitive electronic element that whenever light hits, it creates an electronic signal. So we wanted to see basically how far we can go in solving problems by using one or a bunch of these really, just one by pixel camera. So we get a typical robotic agents, so far in simulator, but now we are working on doing it on real robots too. We basically got a robotic agent. The robotic agent is typically have a camera, like the conventional solution, but we put a bunch of like photoreceptors, for example, 2 photoreceptors on this robot at the strategic places. We'll discuss how we find this a strategic place, but at the strategic places. And then we'll see how well it basically works in solving active tasks. So the robot with the reinforcement learning pipeline is trained to go from here to find a target visually, do obstacle and avoidance, make it there. Everything has to be done visually. So we wanted to basically see that if in the reinforcement learning pipeline, I'm summarizing at high level, in the reinforcement learning pipeline, if the state of the world comes from, instead of coming from this, it comes from these simple sensors, how far we can go. And turns out actually you can go surprisingly far. So this is one example, qualitative example before I move on. So this is an agent that is solving a navigation task, starting from this point, going to, that's the target point. And here is, if the agent had two, well, let me explain the photoreceptor first. So the agent has 2 photoreceptors. Each of them has a 4x4 grid. So this is all that the agent sees. There's nothing else. That's all the sensing of the agent has. And these are corresponding camera views for you, because, it's very hard to make sense of what's going on here. But you can see if these photoreceptors were full cameras, this is what they would be seeing, basically. So I can see that, yeah, well, obviously there's a pattern, it's doing something, it goes around, the obstacles, and you can see it over the map too, and makes it to the target, which is that green ball. All from this, which appears very impoverished, but clearly it solves the problem and it's good enough. And we tested this for continuous control tasks too, like the walker and reacher and the DeepMind control suite. And generally, again, as a summary, it turns out for many tasks that we evaluated, indeed, these simple photoreceptors, a collection of them, are effective for solving many active downstream tasks compared to cameras. And I mentioned multiple times that it now matters where to put these photoreceptors, and that actually does matter. Basically, they have to be designed. So these placements of photoreceptors, they are themselves the outcome of a computational process, which basically finds the role of it is that it's basically a machine learning pipeline that learns to predict the location of these photoreceptors in a way that the performance is maximized for the downstream task. And then that runs basically in the loop. So the reason, well, this was a basically empirical observation for us, that when you have very few photoreceptors, very few sensing points, it now matters where you put them, strategically speaking. So we had to develop a optimization-based pipeline to find the place of these and so on. If you don't do these strategic placement, even though they look random, but they're not random, because compared to random, the performance is very different. So there is something about it, but it's just unintuitive to us exactly why. Despite the fact that, well, obviously there will be some noise in it too. So if you don't do the strategic placement, you can see it in these bars. These bars are different designs, starting from nothing visually useful to the best. And you can see that there's clearly a wide spectrum among different designs. So you have to really try to find the best one, which involves an optimization and so on. So yes, the strategic placement matters. So overall, in the original questions that how far simple sensors can go, the answer seemed to be pretty far. We have just wrapped up this project. There will be a tutorial at CVPR, dedicated, a full-day tutorial to this topic. So if you're interested, drop by there. We're going to have a full discussion about it. OK. So the last part that I want to discuss is multimodality. So one of the properties of active agents is that, again, there's no single agent that in the biological world that actually is a single modal agent. They are always multimodal. They have multiple sensors and so on. And as humans, we are also very multimodal. So this is like a quick demonstration of how you use multiple of your senses to solve a problem. So here the person, we can see a person saying ba. Ba, ba, ba. Ba, ba, ba. And a different one. Ba, ba, ba. Ba, ba, ba. So the majority of you would say the left one was ba, B-A, and the right one was ba, V-A, right? And well, we are not going to run the test, but statistically speaking, 70% of you would agree with me. But what happened was that actually both of these had exactly the same sound. The sound was ba in both times. But in one time, vision was ba, and the other one for vision was for ba. So even though you were exactly hearing the same thing at heard, just the signal that you were receiving from the other sense was impacting what you decide what you're hearing. If you don't believe it, you can actually see it here. You can look at the left one at any time you want. You can look at the right one at any time you want. If you look left, you think what you're hearing is ba. If you look right, you think what you're hearing is ba. Ba, 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 ba. So, oops. I said it the other way around, ba and ba, but I think most of you probably have experienced the effect. So it's a bit, confusing, but testification to the fact that there are multiple modalities in play. Ba. So enough with that. So generally, being multimodal has been quite heavily studied in psychophysics. There are these famous paper, 6 Lessons by Babies, that is from developmental psychologists that have lessons for artificial intelligence researchers in terms of how to develop intelligence. And the first lesson is basically multimodality. And I think there's more than just there are multiple senses. There are more specific things that can be done. Let's say if you have an apple, you can see it. So that's one sensing point. You can touch it. That's another sensing point. But since both of these are rooted in one underlying reality, they basically have some redundancy, some shared information between them. So if you have one system that can just simultaneously sense the world in 2 different ways, you can start learning these basically arrows, which are instances of cross-modal learning. We can learn to go from vision to touch and back, and these would be good encodings of each other, while we don't really need supervision for it. So it has basically learning and calibration value as well. At least that's a hypothesis. So we have been working in this area on creating multimodal foundation models. Just to make sure I describe what I mean by a multimodal foundation model in this context is that there is a world, and we take a picture of it, and we can sense it with depth. We can, another 3D surface normals, put a box around it, and so on and so forth. So every one of these things are a modality that describes the same underlying reality. And what I mean by a multimodal foundation model is that one single neural network pipeline that can receive any of these modalities and spit out any of the other ones. So learn the relation between them and so on. So it's basically an any-to model, any-to-any model. All right. So to give you an idea of what enabling mechanism let this happen in the first place was that there's this concept mass modeling, for example, LLMs, the next token prediction, a version of this idea. And so basically it means that you receive an image in the context of vision, you drop some patches, you predict what the rest of the patches were. So by solving this sort of completion task, you learn about what some underlying patterns in the world are. So these are that the model does learn it. These are the inputs, and these are the outputs. You can see that it's quite close to the uncorrupted image. So I can turn this idea in a cross-model way too, and that's the first version that we did. So you can have the same pipeline that I showed in mass modeling. There's an image goes in, gets some parts of it go away, and we predict what it is. But in the same model, you can do it for other modalities like depth and segmentation, or you can do it for cross modalities, giving complete RGB, get complete depth out of it, and all combinations. So we train it with all of these possible pipelines. In a way, basically, the modalities are being masked out now too, not just image patches. And this was the single model that we trained. So indeed, it does work in the sense of solving the modality agnosticity problem. So what you're seeing is in the first column, independent of what goes in the network, bunch of RGB, no depth, segmentation, and it keeps changing. The reconstruction of the network remains more or less stable, which means then the network predicts the same version of the world independent of how it was sensing it. So in interest of time, I skipped this part, but there are nice visualizations of this on a web page if you want to interact with it, about how to probe these models. So since the first version of multi-MAE, we've worked with our partners in industries, specifically Apple, to scale it up. So the new model is called 4M. We released it a few months ago. So it's basically a gigantic to-token mapping model that receives a sampled set of tokens from any of its sensing modalities that is now around tens of them, basically, 20-something. And all of these modalities are now tokenized too. So you randomly sample a bunch of tokens, you predict another random bunch of tokens, and that's the way we train it. So we scaled it up and so on. So that's 4M. The outcome of it is a model that can solve quite several computer vision tasks out of the box with a competitive performance in a self-consistent way. These are, you can see it, caption, bounding box, segmentation, depth, normals, edges, segment, and so on. This is another one. There's some humans sitting there, so now there's human activated, and so on and so forth. So I mentioned that what we want is to be able to map any modality from any other modality. So besides getting one RGB image and predicting things out of it, is basically there's a full matrix of going from any of these modalities to anything else. So this is the actual full matrix. I think there's 225 of these windows there. Each of these are basically one mapping job. So classically, we would have to use one neural network for each of them. So it would be 225, but there's one model that is solving all of it now. And that was, if that was too small, these are like a more zoomed in version of it. That you can see that from any of these input modalities, 3D, bounding box, or text, we can go to any other ones. So we probe these representations also to see how well the model is learning what it is learning. For example, here, the input to the model has been a bed and a bicycle, 2 bounding boxes. And we asked the model to generate an image for it that conforms to it. And the bed is always in the same location, but the bicycle moves around. So you can see that depending on where the bicycle is, the model generates an image that is sensible. It basically consolidates the context. So if the bicycle is in front of a bed, it just puts a bicycle in front of a bed. But if the bicycle is like weirdly elongated and up on the wall, well, there's no wall, but it decides that I'm going to put a wall there, I'm going to print the bicycle as wall art, and then keep the bed where it was. So it consolidates the multiple pieces of information that comes in. So here's the same thing over video. So you say a photo of a studio bedroom with studio light, and you give it, it's a multimodal model, so you can give it multiple conditions, and you fly around the bicycle. You can see that there are 3 pieces of prompt, and it always conforms to it, but then the rest of it, it makes sense of somehow what context would be more possible, and this is learned from the data. Well, the same thing, this time for cups. So the model allows you, because it's multimodal, to do grounded generation. Like if you want to generate an image that is a bowl with fish and a bowl with rice, but you also want the 3D of it to conform to, for example, to look like that, or you want the placement of the bowls to be exactly like that. Or you can get them from another image in the first place. So you can get this image, say that keep the placement of the cups the way they are, the bowls where they are, but turn it into a bowl with fish and a bowl with rice. And the model can do it. Again, these are all organic out of the box because it's a single multimodal model. I'll skip some of these visualizations in interest of time because there's an unescapable part in the end that, but you can control. You can control the balance of weights across these different modalities as well. So here, a oil painting with a blue flower and depth, but this slide bar says how much the model should conform to depth. Here is relatively tightly, the flower has the same. But then once it went to the left, you saw that they seem seemingly irrelevant to the depth. More steerable generations, not going to get into details of it, but you can use any of these modalities to basically whisper to the model what you want to generate to make it less cluttered and more cluttered and conditioned on segmentation and so on. You can do multimodal retrieval, obviously. Again, this is a single model whose representation is meant to be agnostic, at least some of its predictions. So you can basically express your query in any modality and get them in any other modality that you want, or mix it with two different modalities. Give me images with this mountain scene, but once when it's green and once when it's gray in terms of color palette. And you can see it follows that contextually pretty well. So these are the current modalities in 4M. There's text, there's edges, RGB, a bunch of neural network feature maps, metadata, and so on. And we're hoping to add more embodiment-oriented modalities like motion or motor control and so on. And in terms of data sets, everything that I showed doesn't require one data set that is annotated with all these modalities. We basically pseudo-label all of them using state-of-the-art models. For example, for 3D-oriented modalities, we used our past work, Omnidata. So these were all trained even with pseudo-labeled data, not complete annotated data. I'll skip this fun part too about gorillas and so on. But long story short, I think in the context of even these models that are progressing, I think the looking correct versus being correct, it remains to be a problem, even though in this, I don't have time to talk about it, but I expect that also to hit image models as hard as it hit language models. So to summarize, I basically discussed a single model is a versatile multitask model to solve multiple problems. And ultimately, what we want is to be a model of the world that we can use as a foundation to, on top of it, build other more high-level functions. So we really want to, in the future, learn more from videos. So not at the pixel-to-pixel level, but more, this is the timeline of Lord of the Rings in one shot. So these are hours of visual data. But this gives you an understanding that, hours of pixels doesn't give you. So we want to understand, ideally, a video at this scale, not at the next 2 seconds scale. It'll be interesting to do this learning in a more abstract space rather than pixels. Obviously, if you want to have temporally model long data or any kind of long-range dependency, you have to do it in a more abstract space to increase the chance of success as opposed to high-dimensional observation. So you would think that, well, if you're an autonomous car, you don't want all the pixels. You want to look at the world at this level of abstraction. So generally learning in this space rather than original pixels. Maybe our foundation models can play a role in providing this interface to other applications. And one thing that I think also important is physical supervision. Like I said, every one of the devices that we have are multimodal. So if that cross-modal learning supervision actually becomes effective, we can use them to supervise nearly any device that we have. And lastly, I think I would be excited to understand vision as an emergent phenomenon better. So vision in the natural world didn't come about the way we are developing computer vision. We are engineering it component by component and directly. That's not the way it happened in nature. vision emerged as a result of an agent interacting with its environment, trying to solve problems, and surviving eventually. So it's more like an emergent phenomenon if you want to understand certain aspects of it, rather than engineering it component by component, which will be successful, but it won't. Will omit part of the picture. So I'm hoping to work on this in the future more directly. So before I end, there are a number of people that I would like to bring up. So first, our lab at EPFL. There is supposed to be something there. Well, then I'm gonna, okay, something happened. Anyway, so VLab, these are well, first of all, this is one version of us. This is another version of us that Rudiger already ruined, and so thank you. What I wanted to show is that you can pick according to your style. So really, the people in this picture are the ones that are doing the work. I'm one member of the lab, so I can contribute more or less as much as one person does. And when I'm talking, these are the people that are doing the work, so thank you so much. I appreciate it. Hopefully you're having fun as well, like me. So, and EPFL and IC. Again, one version and another version. You can recognize this gentleman from, in case he's a little bit too, covered. And this is a really nice picture. And so, well, obviously everything that we can do is because of the support that IC and EPFL gives us. But I think beyond that, I personally feel lucky to be part of this group. They say if you're the smartest person in a room, you're the wrong person. You're in the wrong room. And I really have not felt I'm in the wrong room in any IC meeting, and I really mean it. There are most of them with their accomplishments, with who they are, with the background, make me feel really like an imposter being here. So definitely I feel lucky and honored. So thank you for that. And the people and groups that have contributed to my education and really everything in the past at Berkeley, Stanford, UCF, all the works that I showed are teamwork, so I really benefited from great collaborators. I'm not going to name them one by one, but I really remember all of them one by one. And also special thanks to my advisors, Jitendra, Silvio, Leo, even though like some of them are like close collaborators, but they were really more like an advisor to me, secondary advisor. Jitendra, Silvio, Leo, Mubarak, Rahul, thank you so much. You really have impacted me. And last but not the least, my loved ones, my family and friends, especially my parents, my brother, my niece, my sister-in-law, and friends. So most of them are unfortunately not in Switzerland, so they're not here, but I see some lovely faces in the audience. They are the anchors of my life, my loved ones, and every time I feel sad or anxious or depressed or anything, a quick phone call to any of them, is just a very effective remedy for me. So thank you so much for being in my life, and that's it.